Okay, lecture 18. A little under the weather. I had my flu shot over the weekend and I still haven't fully recovered from that. So I apologize. Finished strong. You'll find that most students kind of give up at the end of the semester. If you finish strong, there's some real benefits to that, to your grade and to your learning. So this is the time of the semester where things tend to fall apart. So you keep working, keep focused, get your things done. There's some real benefits to that. So don't forget your student success seminar assignment. Thursday, we'll continue on ration balancing. Your petitioning of the dry matter assignments too. So this week is how to be a professional with Tom Paluski. That's a real good presentation. He's been doing that for a long time, and he's there's some real benefits to going and watching that one. So this week, you guys are set. Okay. So last time we talked about fats. Different ones we'll measure. Most of the time, you're going to deal with crude fat on a farm. You'll total up, or your person that balances your rations will total up your total fatty acids to make sure they don't go over a critical limit. If you go over a critical limit, we'll mess up the rumen and lose all the gains we might have gotten with the fat. So the others are more research-based. The total triglycerides, the individual fatty acids, and we don't do those or don't need those on a regular basis on the farm. So feeding fat, we have some upper limits with our cows. We're not like pigs or the geese and stuff where they can really overfeed the fat and still do all right. Our cows, there's kind of an upper limit to what we can do. They're not designed to process fat. They're not designed to handle excess fat. It's not normally what they would have in their diet. So So who feeds fat? Which animals do we need? So lactating cows, we're going to feed fat in an attempt to get more energy in the diet on a per weight basis. There's more than twice the energy on a pound basis, 2.25 times. So we have to account for all that fat coming in. So we talk about basal. So usually the stuff that is just kind of background. So the plant will have a certain amount there. We can think of just the lawn out here would have 3% fat. We call that basal. And then we start to kind of figure in start to account for the added fats that come in the diet. So anytime we have oil seeds, we're going to have additional fat in the diet. So soybeans, cotton seeds, any of those oil seeds will add fat to the diet. Byproducts, usually there's an enrichment of that fat in the byproducts. So we have to account for that fat there. And then we'll talk about the manufactured or ruminant inert fats. So they're a separate class. They're supposedly inactive in the rumen. There is some arguments among scientists about whether that's true or not. So who gets fed fat? Calves. We tend to feed them fat, especially in the winter. They can use that extra fat as they're starting to grow as additional sources of energy to keep them warm in the winter. Heifers, there's no reason to feed extra or additional fat to a heifer. It's not cost effective. Most of the time, we're trying not to get our heifers too fat anyway. Adding more energy to the diet is not going to help us or help the cows out. So we do not feed additional fat beyond the basal to our heifers. Dry cows, we do not feed additional fat to the dry cows. We already have enough issues with ketosis, fatty liver, and things like that. We don't want to add that in to the dry cows' diets and exacerbate those situations further. You might give them a little taste so they're ready on the other side, but we're not putting it in for energy basis there. They can, both heifers and dry cows can eat more than enough of their energy needs with just basic forages. Lactating cows, yes, we feed additional energy in the first part of lactation. There's some real benefits to that. When intake is limited, we only have so much dry matter to get in. Putting a little bit more density in there can help those animals along, minimize their negative energy balance, get better peaks. So we talk about early and peak lactation to help them with that negative energy balance so they don't drop quite as much. And then if we got some real thin cows for whatever reason, we want to rebuild that body condition. We might add some fat to the diet in later lactation as we rebuild that body condition and get those animals ready for the next time around. So when we account for lactating cows, we're going to have the basal added and rumen inert. And what our rules of thumb related to that. We have upper limits as to what we can do. The general thought is we can do a pound or a pound and a half from each source. Pound, 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 and that's about the upper limit of what we can do. That's probably a lot, especially if you're thinking about that rumen inert. We do a quarter to a third of a pound of rumen inert up the dairy, and that's about all you really want to do. That pound to pound and a half works out to somewhere in that 2 to 3% of the diet. So if you add up the 3, 3, and 3, you're going to have 9%. So 9% is about as much as we could do if everything was perfectly balanced and we only got 3% from each of the areas. That's about as much as we could do. Beyond that, we start to run into problems of rumen function and a number of other things about fat metabolism stuff. Cows are just not designed to handle fat in their diet. We think about pasture, there's not a lot of fat in there. They're designed to have something that's fairly low in fat. So what are the advantages of feeding fat to a lactating cow? We're going to have increased energy intake. If they have the same dry matter intake, we replace some carbohydrate with fat, we should get 2.25 times as much energy for each substitution we do with the fat. So we're not going to do all that much, but we do get a few extra calories in there, and that's helpful as those animals try to go through early lactation, try to get to peak milk production. So fat can give us increased energy intake, more megacalories in. That should mean less body condition loss, more body condition gain in late lactation, less loss in early lactation. And we know that certain fatty acids can aid in biological processes and or be essential. We've mentioned the essential fatty acids. They are necessary for proper animal function, proper animal health. We've got to get those in one way or another. Normally, that's not a problem. If they keep their forage diet, those fatty acids are more than well covered. So we know there are certain manufactured fats that have certain profiles of fatty acids that they say, well, this is better for reproduction if you make sure these fatty acids are present. Megalac R, I don't know if that's a product anymore, but when it came out, it was meant to help enhance reproduction. So the R is for reproduction. The certain fatty acids were meant to generate a more viable egg and hopefully a more viable embryo by putting the right selection of fatty acids in place. Disadvantages. So this is where we have to be careful. So disadvantages for a lactating cow, we might compromise rumen function. If we have too much, we got to have a certain amount of basal. If we add too much, the stuff in the middle, not the rumen inert, but add too much added fat, you're going to reduce fiber digestibility, may cause milk fat depression, may overload the liver. So if you put too much fat in the rumen, you will it's thought that they have problems with the microbes adhering to the fiber so they can digest them. I don't know if that's actually what happens, but that's the general theory. So if the microbes can't attach and they can't digest the fiber, By putting in that fat, you've decreased the fiber fermentability, the fiber digestibility, and you've actually lowered the digestible energy for that feed. So that's not a good thing. So compromising rumen function, lowering that fiber digestibility. We get too much fat in the diet. We overload the rumen. We mess up the fermentation. That's going to lead to a series of signals that are going to tell the mammary gland to shut off. If certain fatty acids get by the rumen, the unsaturated ones, they get absorbed, and the mammary gland responds that if this is absorbed, something's not happening well, or something's not happening good in the rumen. So we're not taking care of ourselves as much as we might. So we have to basically say the calf, you're on your own. So the cow reduces the fat output to take care of herself, Joe's rule number 1, and compromise the calf in the short run, not giving as much energy to that calf, because I need that energy to stay alive. You put too much fat in the diet, you can also overload the liver. That leads to fatty liver that predisposes that animal to ketosis, inhibits liver function, so creation of all the things that the liver creates, and particularly glucose, that will be compromised. As a general rule, cows do not like the taste of the fat, so that's not something they crave. That's not something they want in their diet. Particularly the manufactured ones, the smell of that, whatever that fat, burger fat or whatever it was, they all smell the same way. Megalac, Energy Booster, they all smell the same way. Cows tend to turn their noses up to it. So it comes down to a cow is not designed for a high fat diet. So overdoing it is going to mess things up. Any questions about fat in our cows? So moving on to protein as a nutrient. We've alluded to this a couple times. What's the key difference between carbohydrates, fats, and protein? And the key difference is the nitrogen that occurs in protein. There's no nitrogen in carbohydrates. There's no nitrogen in fats. So the presence of protein, of nitrogen, specifically the amino group attached to the end of the amino acid. One end of it's an amino group that has nitrogen in it, and that's what separates protein from all the other nutrient classes, particularly the fat and the carbohydrate, is the presence of nitrogen. So what we do with protein with our dairy cows, and certainly a lot of the chickens, the pigs, they've gone to balancing on a amino acid basis, getting more specific than just crude protein. We're still in that crude protein category. We're starting to move into the amino acid area, but the complication of the rumen, what happens there, what happens in the rumen is so hard to quantify, so hard to predict, that we're still kind of back at crude protein. So crude protein comes from nitrogen. We measure the nitrogen in a feed, and then we multiply it by 6.25. That is based on the fact that on average, most of our feed animal proteins are about 16% nitrogen. So if you take 16 and you divide it into 100, it'll happen 6.25 times. So if I take my nitrogen content, multiply it by 6.25, I will get the total amount of protein, more or less. So 6.25 is what we usually use for the feeds. If you're working in a milk lab, it would be 6.38 is what you multiply it to get the crude protein in milk, although most places do true protein anymore. They've found ways to measure protein directly. On average, our feeds there, so crude in the sense that it's a rough number. So nitrogen times 6.25 equals crude protein. And in this case, crude means it's a rough measure. We have more or less that amount of protein in our feeds. So we mentioned urea in our feed ID, 270, 80% crude protein. Urea is 46% nitrogen. If I multiply that out, I get 282% crude protein. Now, is that actual protein? No, but it's where we come up with, and that's, I guess, illustrates how we can go wrong with this. There's no actual protein in urea, but if we base it off the nitrogen content, the bacteria can turn urea into protein, which is what we hope they do with that present there. So atoms in protein, we've got the carbon and hydrogen, we've got the oxygen, we've got nitrogen, we have traces of sulfur, and we have phosphorus now and again, depending on the amino acid we're dealing with. So for a lot of our animals, the only reason they need sulfur is to make those specific amino acids related to the sulfur needs. So if we're looking at crude proteins, some of these should be familiar to you. NRC 2001, their feed library, alfalfa silage, they list as 22. That's pretty generous. I think, of course, we have a lot of, that's pure alfalfa. We have a lot of grass alfalfa mixes, so that would be a lot less. Alfalfa hay comes in at 20% crude protein. We probably lost a little bit of the leaves there. So we've lost some of the protein when we're making that hay shatter. Those leaves end up on the ground. Mixed grass hay, 15 is a fairly good number for crude protein for a mixed grass hay. You get it early enough, it hasn't headed out yet, you should be able to get in that mid-teens number. Corn silage, they have an average of 9. Ground corn, very similar to the entire plant at 10% crude protein. And then we had corn gluten meal, corn gluten feed. Corn gluten meal has most of the protein at 65% crude protein. Corn gluten feed has most of the fiber, but there's still some protein in there. Not a bad source of protein either. beet pulp. NRC listed as 10. I think most of the time it's lower than that. Whole cottonseed, 24. High moisture shelled corn. Very similar to corn grain. Barley, a little less starch, a little bit more protein. So 12% crude protein. Soybean hulls, 14%. Soybean meal, 48% crude protein, 54%, and these are on a dry matter basis. So on an as-fed basis, soybean meal 48 is about 48% crude protein. If we take the water out, that crude protein enriches to 54. So you'll find that a lot of the pigs and the chickens, they tend to do everything on an as-fed basis because everything they feed is pretty much the same water, moisture content, same dry matter content, about 90%. So doing it on an as-fed basis, it's easy to do. So we're thinking about feeding our animals protein. We need to think about pounds per day. If we're looking at 17%, 18% crude protein, we're looking at 10 to 12 pounds of protein in our Pen 2 group up there, eating 65 pounds a day. So pounds per day to support all their functions, keeping them alive, continuing to grow, lactation, pregnancy. We need pounds a day. And we're looking at protein. What really matters is what the proteins are made up of. And that would be chains of amino acids. Think about those as Lego blocks. We got all the different Lego blocks to make different things. Different amino acids have different functions, different purposes. Those chains can be broken up, and they are broken up if they're digested and then absorbed. And then the amino acids become the building blocks for whatever the cow needs. So enzyme purposes, protein is probably a pretty good part of the body. So proteins are going to be involved in all the structures of the body. Most of the volume in bones is protein. All our muscles are protein, all our skin structures, organs are made up of proteins. Enzymes, the things that kind of run the body, the catalysts that help things move faster, that make the chemical reactions occur in our body on a rate that keeps us alive. Those enzymes are made of proteins. And then we have a number of different packages in the body that are made up of proteins. So we think about the carriers for iron, the carriers for copper in the blood. Those iron floating around free, the copper floating around free is pretty nasty stuff. And we put them in those carriers to protect the body from the harmful effects that those things can have. We also carry fat in blood in protein packages. So the outside of the protein or fat carrier is hydrophilic, That means it can move through the blood pretty easy. Fats are hydrophobic. They do not dissolve easily in the blood. So putting them in a carrier to transport them where they need to is a whole lot better as a system than just letting them float freely in the blood. So we're thinking about protein. Plants can synthesize all of their amino acids from scratch. That's kind of necessary. They can't go around and collect those amino acids like animals or insects might. So being able to manufacture what they need, as long as they have enough nitrogen, allows them to get done what needs to be done. Microorganisms can also synthesize all of their amino acids from scratch. Again, they don't have a large range of motion. They're not going to cover huge distances to collect those amino acids. So they need that ability to synthesize amino acids and basically get done everything they need to get done. If they have the raw building blocks, energy, carbohydrate skeletons, and some nitrogen, they can build everything from scratch, just like the plants do. Animals have decided that, okay, I'm going to depend on something else to provide me with the amino acids I need. I retain the ability to do about half of my amino acids, but the other half I'm going to depend on what I get from my diet. So we need to consume those amino acids if we're going to get maximum performance, maximum health for that animal. So we divide amino acids for animals into what are called essential and non-essential amino acids. So essential amino acids are those that can't be synthesized at a rate to provide normal growth. So there are about 20 amino acids we count on for the body. About half of those 10 fall into the essential amino acid category. Non-essential, they can be synthesized by the body. Usually the liver does most of the work. So having that there allows the ability to do that. We can make those other 10. So what we'll hear about a lot of times is the limiting amino acid. We've discussed this before. The limiting nutrient for an animal, the limiting amino acid is the one present in the lowest amount relative to its requirement. So we're finding that if we add supplemental methionine or lysine to a lactating cow's diet, we actually get more milk production. A couple grams of that amino acid actually leads to pounds of milk production. It's pretty amazing the efficiencies that are gained by just a small addition of one of the required amino acids. So if that is the case, we add that lysine or methionine to the diet and get more milk production. That is the limiting amino acid at the moment for that particular cow. So we find those limiting for our cows. So small additions can get us more production. So we're looking at our amino acids, lysine, methionine, and tryptophan are all amino acids. They're likely to be limiting in diets for monogastric animals. So we have to make sure with our pigs and our chickens and our horses that we provide those amino acids in the proper amounts to make sure that they get their full protein nutrition. So we're looking at proteins, about 20 more or less amino acids are found in nature in our dairy cows. As we said already, 10 essential, 10 non-essential. So they're all necessary for life. So this essential is probably not the best word to use. They're all necessary for life. They are essential in that they must be provided to the small intestine to be absorbed by the animal. So we can either put them in the diet if we're a pig or a chicken. We put them in the diet, they get to the small intestines, they get digested and absorbed. With our cows, we can have amino acids from the diet and amino acids generated by the microbes in the rumen. Both of those become the amino acids the animal has to live from. So if we're looking at our proteins and specifically our amino acids, they all have the same blueprint, same basic form. We have a carboxyl end, which is carbon atom, double bond to an oxygen, and then an OH group on the other side. We have a middle carbon with an R group off of it in the middle. Then we have an amino group at the other end. So all amino acids will follow the same basic blueprint. What's different is the R group for all of our amino acids. And the R group tells us which amino acid it is. So what's different is the R group. So that R group can be anything from just a simple hydrogen, one atom sticking off, that's glycine, to some huge attachments of multiple rings with all kinds of different stuff stuck to them. And those R groups confer the chemical properties on each amino acid and kind of helps us determine, or helps the protein determine how it's going to fold up, how it's going to structure, how it's going to lay out for that. So the generic amino acid, you got the R group sticking off the middle carbon. So you have this backbone of carbon, carbon, nitrogen that goes through a protein. And then you have R groups sticking off in a number of different directions. So if we're building a protein, we put the red dots here, the red dashes. That's our definition or divider for our amino acids. So NCC, that's chain that goes through all of the hydrogens, or all the proteins. And then we have our R groups sticking off that middle carbon, or that carbon in the middle of the thing there. So individual amino acids put together in a string. So when we're looking at a backbone of the protein, we'll have often thousands of amino acids in the chain, and the order in which they're put in, whatever amino acids they select, will determine the character and structure of that particular protein. So we have a amino acid and another amino acid. They're going to be put together in a dehydration reaction. So we take a hydrogen from the amino group, the OH from the carboxyl group, and we form a bond and we lose water. So dehydration, we lose the water out of there. We form a peptide bond that forms the string of amino acids as we go together. We're not going to ask you to remember these structures, but I did want to introduce them. So these are the 20 amino acids that we deal with. So you have glycine up here, which is just a hydrogen ion. These are the R groups potentially for all amino acids. They'll fall into three categories: hydrophobic, those that don't like water, the R groups; hydrophilic, those that like water; and some that kind of are in between, depending on what the environment is. So if you look at the hydrophobic, you'll notice it's dominated by the black carbon and the white hydrogens. So except for this, nitrogen right there, these are all hydrocarbons. Hydrocarbons tend to be, well, they are hydrophobic. So we think about oils, gasoline. Those are all hydrocarbons. Whereas you look at the hydrophilic ones, you see a lot more color. The red is oxygen, the blue is nitrogen, yellow is sulfur. So the what we're having is an unequal sharing of the electrons, which makes these groups, they have a charge associated with them. So the charge makes them water soluble, hydrophilic. They like water. So these are going to twist the chain of amino acids toward water, whereas these are going to turn away from water. So we have water as a solution that all our proteins are in. How they react with water determines their shape. So I don't think I printed this out for you, but we'll get that to you. So non-essential amino acids, we're not going to ask you to remember those. These are all the ones that the body can make. What I am going to ask you to remember is the essential amino acids. These are the ones that the body can't make in sufficient quantities to maintain health, maintain growth as we go through. So there's arginine, histidine, isoleucine, leucine, lysine, methionine, phenylalanine, threonine, tryptophan, and valine are our essential amino acids. So these are the ones we focus on with our dairy cattle. Lysine, methionine are the two that we have gotten enough knowledge that we can add those to the diet and get responses, or at least think about or know when we're going to get decent responses. So these must be absorbed in sufficient amounts at the small intestine. So the reason I say right there is those amino acids can come from the diet, or in the case of our cows, can come from the rumen. So the microbes themselves manufacturing that protein, turning carbohydrates and a nitrogen source into microbial protein. The cow can live off of that. So that's a real advantage if we can take balance the rumen to get maximum protein production, and then that protein is digested and absorbed at the small intestine. So lysine and methionine are our two that we run into most often with limiting milk production. So you'll see protected lysine protected methionine added to our dairy cattle rations. They are not altered or touched in the rumen. They pass to the lower tract. They hit the acid of the abomasum and they are freed so they can be absorbed and used by the animal. So how do you remember those? There's a couple of different mnemonic devices that people use. If you take the first letter in each of these, you can do Private Tim Hall, Private Matt Hill, or the one I use, Fill Empty Vat. So P, phenylalanine, V, valine, tryptophan, threonine, isoleucine, methionine, histidine, arginine, leucine, and lysine. So how do we manufacture our, how do we measure our proteins? So we've alluded to this crude protein. We do what's called a Keldol. Good German name. Keldol nitrogen. We go put the feed through a series of steps. Basically, we're boiling the feed in acid, and we reduce it down to its components, free everything up. Through a series of steps, we turn that nitrogen into something we can measure. And that Keldol, we multiply it by 6.25 and we get our crude protein. So this is a Keldol system. So I've actually done some of these. Most places don't do these anymore. A, they're time consuming and tedious. B, and they're dangerous for another one. Usually when you're in the Keldol room, you got a full face shield and gloves and apron on. So we take the sample, we put it in sulfuric acid, and we boil it under heat for a certain, I can't remember the time off my head, but we basically turn all the nitrogen into amino groups. Then we take that solution and we back titrate it to figure out how much nitrogen is there. So it's an indirect measurement, but it's if you got a good touch, you get a fairly accurate number. And we measure that nitrogen and then we multiply out how much is there. So that gives us our crude protein. So we'll stop there today. Any questions?